So tonight we'll look at log problems, and we'll start with a review of logs. So last class we looked at exponential equations and how we can change those into log form. So 27 to the 2 over 3 equals 9. We know that's true. We could also write this as log to base 27 of 9, which would equal 2 over 3. And so these two equations are equivalent. They mean the exact same thing. And we looked at how the 2/3 here is an exponent. And if the 2/3 is an exponent, then what happens here is that this log to base 27 of 9 must be an exponent. And so if that's the case, then there is going to be some laws that apply to logs. The first one was that when you're multiplying arguments, we could write this as the addition of logs with the same base. Or conversely, if we have the addition of logs with the same base, we can keep the log of the base and multiply the arguments. We also have the division of arguments. If we have the division of arguments, we can write that as the difference in the logs of those arguments. Or we could say that if we're subtracting logs of the same base, then we can keep the base and divide the arguments. And the third law was that when we have an exponent on the argument, we can bring that exponent down in front. And it becomes multiplication. So logs are taking everything difficult and making them into everything easy. Multiplication becomes addition, division becomes subtraction, and powers become products. So we got stuck on this problem here. A bank account earns interest compounded monthly. I'll stop right there because as soon as I see the word compounded, I'm going to the compound interest equation. And so we had y equals the initial principal amount, A naught or P, it doesn't really matter what you call that, times 1 plus the interest rate in a decimal form divided by the number of times per year is compounded and raised to the number of times per year is compounded times the time in years. So when we plug this into our equation, we had y equals 400 times 1 plus 0.042 divided by 12 to the 12t. And the question asks, when does this double in value? So our y value would be 800. We're looking to solve for t. And so this is an exponential equation because the unknown is in the exponent. And we can't get a common base even after we isolate the power by dividing both sides by 400. So we're stuck. But we know that we can take the log of both sides. As long as we do that to one side, as long as we do it to both sides, we can do that. So we'll write log in front of both. That really changes everything, right? This is no longer a 2, this is log 2. And so what happens here is now this enables me, because there's now logs, this enables me to use the down and front rule, where I can bring that 12t and I can bring it down in front and make a multiplication. Now I can divide both sides by the 12 log 1.0035, and I solve for t. So this account will double in value every 16.53 years. No matter how much money it is, it's going to double every 16.53 years. So what we've seen is that we had this equation, and we wrote it like this. So that means that we could set up a shortcut. Instead of taking the log of both sides, we can write the exponential equation as the equivalent expression in log form, and that must be equal to this expression here, this equation here, which is what we got when we took the log of both sides. And so what you're going to do here, this is the changing bases. This is base 10, and so is this. And what I want you to remember is that the base goes on the bottom. So we're going to divide the logs, putting the base on the bottom. Okay, and so that's easy to remember, the B and the B here. A student once tell me that the basement of your house is also on the bottom of your house. So, oh, that works too. So now we can very quickly evaluate any log function. For instance, if we had this equation, 2 to the 4x minus 7 equals 40. I'm stuck in exponential form. I can't get common bases. So I'm going to go to log form. Log to base 2 of 40 equals 4x minus 7. All I have to do now is change the base. Just remember that the base is on the bottom. Log to base 2 of 40 is the same as log 40 divided by log 2. By the way, you can check that out. Just as a note here, we know what log to base 5 of 1.5 is. It's 3. And so you can check that out on the calculator by going log 1.5 divided by log 5, and you'll get the answer is 3. So we see that these are equivalent ways of writing the same expression. And so I can do this with my calculator now. I can type in log 40 divided by log 2, and my calculator can do that. And now I can start solving for x. I can add 7 to both sides, and I can divide both sides by 4. If I plug in x equals 3.08 in here, I'll get an equation, or I'm going to answer 40, which of course equals 40. Here's another question we're asking to solve for x. So in this case, I can isolate the power, but I don't know what 9 to the 4 is. And I recognize here that I can get common bases and simplify the left-hand side of it. 9 is 3 squared, so I really have 3 squared to the 4. So that's a power of power. I'll keep the base and multiply those exponents. And now on the left-hand side, I'm multiplying power to the same base, so I'll keep the base and add those exponents. But that's it. That's all I can do in exponential form. So what I'm going to do now is I'm going to go to log form. I can now evaluate this. Log to base 3 of 100, we can find by calculating log 100 divided by log 3. And now I can subtract 9 from both sides, and I get the answer. Yet another one. Again, I can't get common bases here, so I go right to log form. I can rewrite this as log 2 divided by log 4, remembering that the base is on the bottom. My calculator can give me those answers. And now what I can do here is solve for x. So what I did in this example is that I went to, from right here, I added 3x to both sides. And then I added, excuse me, 1.16 to both sides as well. So 3x plus 1.6 minus 1.6 just gives me 3x. 2 plus 3x minus 3x plus 1.16 gives me the 3.16, and then I divide both sides by 3. And here's another one, a little trickier here. Again, you can ask yourself, if you're stuck looking at this, you can say, well, why am I stuck? I don't know how to deal with this, the x root. So what we have to recognize here is that if that was a square root, for instance, of 17, I could write that as 17 to the 1/2. And if it was the cubed root of 17, I could write that as 17 to the 1/3. So since it's the x root, I can write this as 17 to the 1 over x. And I still belong to base 2, and I still have it equal to 6. Now what I can do, because this is in log form, I can bring this exponent down in front. And so I can multiply both sides by x here. And now log to base 2 of 17 is log 17 by log 2, which my calculator can do. divided by 6. This one is pretty tough to go back and check your answer here, but we could use that in this expression here. Here's yet another question, a little bit different. What happens here is that we've got two bases. Again, I think it's always important that you recognize why one question is different than the other. If you get stuck in something, ask yourself why you're stuck. So if I go to put this in log form, I start with log to base. Well, I've got two bases here. I've got a base of 5 and a base of 12. So I can still do that, but I think it's easier to take the log of both sides. When we take the log of both sides, that enables us to bring the exponents down in front. You have to have a log function to be able to bring the exponent down in front. When I do that, the entire exponent, this 2x plus 7, is multiplied by the log 5, hence the brackets here. Same thing on this side. The x plus 14, all of that is multiplied by log 12. So now I can multiply this out, finding what log 5 is in log 12. I can take log 5 and multiply it by this. Don't be intimidated by the decimals, they're just numbers. If you're stuck, if you are nervous where to go, you could try this. I'll erase this in a moment because it's the wrong answer. But if you had 2x plus 7 times instead of log 5, maybe you just had times 3. Oh yeah, well that looks familiar. Now I can multiply these out. So what we would have here, okay, no, I can't erase. What we would have here is, we know to multiply this out. Just because it's 0.7 or 0.699 doesn't change the math. We're still going to multiply this out. So now what I can do here is I can collect like terms, and I can solve for x. If I plug in x equals 32.2 here and here, I would get two equivalent. These would be equivalent expressions, and my answers would be the same for both sides. So here's some log equations. You might want to give yourself a chance to try these before I go through them. Maybe you can pause the recording and try those. So what happens here is that there's nothing I can do in log form, so I'm going to go exponential. This is 4 cubed equals x plus 5. 4 cubed is 64. Subtract 5 to both sides. I get x equals 59. Question B is a lot more difficult. In question B, I don't know what this log is because I don't know what x is. And I don't know what this is because I don't know what x is. There you go. But what I do recognize is that I have common bases. I'm adding logs at the same base. So what I can do here is I can keep the log in the base and multiply those items. And this is where you start to get really excited because when you see where this is going, I'm going to get a quadratic in here. I'm going to have 4x squared minus x. But that's all I can do with log form. I'm stuck. So if I'm stuck in log form, we're going to go to exponential. 5 to the 1 equals 4x squared minus x. Now this truly is a quadratic, and we know how to solve those. We set one side equal to 0, and we use the quadratic root form. You should recall that x equals minus b plus or minus square root of b squared minus 4ac all over 2a. And so my a value is 4, my b value is -1, my c value is -1. So I plug this in, this, which means x equals 1 plus or minus 9 over 8. And recall that whenever we have a fraction, we have to do the top brackets, or there's implied brackets at the top. This gives me two answers. Now these answers are the answers to this equation. They may or may not be the answers to our original equation up here. So we have to check them. So if I plug in x equals 1.25 into here, I have log to base 5 of 1.25 plus log to base 5 of 4 times 1.25 minus 1. And when I do that in my calculator, I get an answer of 1. So this works. Again, I would do this on the top one here. I would do this as log 1.25 divided by log 5. Here, this is log of this. This is 5 minus 1 is 4. So I go log 4 divided by log 5. When I type that in my calculator, I get a true statement. I get 1 equals 1. But when I go to evaluate x equals -1, I plug in x equals -1 and I get this expression. Log to base 5 of -1. When I type that into my calculator, I know that I haven't even finished this equation, right? I didn't even worry about the log to base 5 of 4x minus 1. When I plug this into my calculator, as soon as I try and take the log of -1, I get an error. This asks 10 to the what gives you a negative number. There's nothing. 10 to the 1 gives you 10. 10 to the 0 gives you 1. 10 to the -1, that just gives you 0.1. And the next 10 to the 2 would be 0.01. And 0.001 would be the next one, etc., etc. You never get to 0, let alone to -1. So this x equals 1 is not an answer for my original equation. Right here. So we have what's called an extraneous root. I'd like you to show me that root, but then I'd like you to cross it out. What that means is it works for this equation, but it doesn't work for our original equation. Here's another example of the quadratic within the log function. Again, on the left-hand side, I have the addition of logs with the same base, so I can keep the logs and keep the log of the base and multiply the arguments. And I can change that into exponential form. That's 3 squared equals x minus 5 times x plus 3. Now I can multiply this out. I have a quadratic, one side equal to 0. This one I actually pick a factor, which is a little easier. I need 2 numbers to multiply to give me -24. And they have to add to give me -2. So that would be -6 and 4. So I can rewrite this in factor form, x minus 6 times x plus 4, which gives me x equals 6 and x equals 4. And I have to check them. When I plug in 6 here and here, I have positive arguments. That one works. That's an answer. When I plug in x equals -4, I have -4 minus 5, that's -9. I can't have that. That doesn't. That's a great question because, of course, it's involving a quadratic inside the logs. Hint, hint, nudge, nudge. That shows up in the file. Here's another interesting question. This is the subtraction of logs. Again, I notice they have the same base, so I can keep the log in the base and I can divide these arguments. The x's do not divide out. Imagine if I had x plus 2 over x minus 5, and I had x equals 10. Well, if the x's divide out, that's 2 over -5. But if the x's didn't divide out, and I plugged in x equals 10, I would get 12 over 5. Clearly, these two are not equal. So you never cancel out or divide out these x's because they're not a factor in the numerator and the denominator. It's in there, but it's not, the entire numerator is not multiplied by x, for instance. So here what I'm going to do is I'm going to go to exponential form. And I see that I have 2 to the 3, which is 8. And now again, you have to solve this for x and say, well, why is this difficult? It's because of this denominator that this is difficult. Well, let's get rid of that. Let's multiply both sides by x minus 5. And when I do that, x minus 5 divided by x minus 5 is 1. So now I can start collecting like terms and solving for x. And I get x equals 6. And so again, I can plug this in up top here. 6 plus 2 is 8. Log to base 2 of 8 is 3. Minus 6 in here. 6 minus 1 is 5. 6 minus 5 is 1. Log to base 2 of 1 is 0. 3 minus 0 is 3. So this works. All right, so let's take a look at some word problems. Joke from the top here. So Sidney Crosby rookie card was purchased in 2005 for $15. Its value is set to double over 2 years. When will the card be worth $90? I was going to say its value is set to decrease by 15% every concussion, but I thought that might be a little bit too soon. In any case, we've set up equations like this before. We see that the value is doubling every 2 years. There's my common ratio. Here's the period. This $15 is what I started with. So the equation is y equals 15 times 2 to the x over 2. I'm going to plug in x equals 9, or sorry, y equals 90. Now I'm going to solve this exponential equation by isolating the power, dividing everything by 15. And of course, it looks like I'm stuck because I can't get common bases, but I'm okay with that now. I'll go to log form. Log to base 2 of 6 equals x over 2. Well, if I put the base on the bottom here, I can evaluate log to base 2 of 6 by calculating log 6 over log 2. Multiply both sides by 2. And so in 5.17 years, the card will be worth $90. And that's, of course, if it doubles every 2 years. If he goes on to score 200 goals in a season, this rate is going to change. But the data that we would have on this, the expectation that we would have is that it's going to double every 2 years. So if that holds true, in 5.17 years, the card would be worth $90. So here's another type of question that we've done before. A certain radioactive element has a half-life of 8.2 minutes. When will there be 1/10 of the original amount? So again, when we see half-life, we're talking about the base of a half. And so, and the period is this 8.2 minutes. And so what we have here is y equals a naught times 1/2 to the x over 8.2. Now looking for when there would be 1/10 of the original amount left, or the y value therefore is going to be 1/10 of the original amount. So I plug that in and I select the power. I divide everything by a naught. And I have this. Am I stuck? No way. I can get I can write this in log form. Remember that the base is on the bottom. Evaluate this, multiply both sides by 8.2. So this means that in 27.24 minutes, there will be 1/10 of the original amount left. No matter what I started with, there's going to be 1/10 of that amount left, since the half-life is 8.2 minutes. So here's another question. Sarah bought a computer for $2,000. Its value depreciates by 18% every 2 years. By what percentage does it depreciate every year? A lot of people will say 9%. It's not actually true. Let's take a look. If it's losing 18% a year, that means 82% of its value is remaining. So that's going to be the common ratio. If you recall, the way that we can get that is as soon as I see the word depreciate, I'm talking about the common ratio is 1 minus that interest rate in a decimal form. So that's 82% of 0.82. So by what percentage does it depreciate every year? This means that x equals 1 for 1 year. So I'm going to plug in x equals 1 and solve. So what this means is the table looks like this. We started with $2,000, we went down to 1811.08, and then I took 18% of the 2,000 and subtracted it from 2,000, and that gives me 1640. And so now I can find the common ratio here. The common ratio ends up being 0.906. Well, that's what we're remaining, so we're losing 100%, sorry, we have 100%, and what's left over at the end of 1 year is 90.6%, which means we're losing, you see here, 9.4%. So even though it's 18% every 2 years, it's 9.4% every year. And because the value changes every year, that's why it's not half the 18%. Not 9% every year, is 9.4% every year. So sometimes you can get tricked. They'll say things like, well, it'll depreciate by half, but it'll take 10 years. You know, that's not 0.5, or that's not 5% every year. That's more than that. So now we can ask question B, which says, when is the value of this computer $99? And so again, we have the exact same equation. We plug in y equals 99. This should be very straightforward now. I'm going to isolate the power. I can't get common bases. I'm not surprised. So I'm going to go into log form. I'm going to evaluate the logs, use the calculator rule, and then I'm going to multiply both sides by 2. So in 7.09 years, the computer would be worth $99. Okay, so here's the last question, and it's a doozy, to be honest. We're going to have two accounts here. So Ben invested $250 in account paying that will double every 8 years. Josh invested $600 in account paying 6% interest per year compounded daily. When will they have the same amount of money? Okay, these numbers are going to look crazy, but you have a calculator. You know, your calculator can handle these numbers. So let's look at Ben's money. Invested $250 in an account that's going to double every 8 years. We can get that equation. Now I put t here instead of x, simply because I saw the word compounding, and I know that in my next equation, the equation for Josh's money, I'm going to have a t. And here's that equation. We saw the word compounded, I'm immediately going to go to the compound interest equation. Now, when will they have the same amount of money? When means we're solving for t. My answer is going to be t equals something. Not a 2, that's supposed to be a question mark. And so they're going to have the same amount of money when their y values are equal. If the y values are equal, then these expressions have to be equal. Like this is what Josh's y value is. This is what Ben's y value is. So we're going to set these equal to each other. And we're going to solve for t. So let's simplify this a little bit. First of all, I'm going to take as many decimals as I can to get this. I'm also going to divide everything by 250. It's not really isolating the power because I can't get rid of this coefficient, 2.4, which was the 600 divided by 250. But I see here that the 250 is the divided. So now that I have this expression, again, I can't go to log form, or sorry, I can't go to, I can't go to log form because I'll start with log to base. Well, I've got 2 bases here. So I'm going to take the log of both sides. I'm going to make this even longer. So I write log in front of both sides. What that enables me to do is that enables me to take this t over 8 and bring it down in front. It does not, however, enable me to take this 365t and bring it down in front. And that's because this 365t is not on the 2.4. So what I have here is this equation, which I can't solve for yet because this is still an exponent and my unknown is in there. So what I need here is I need to be able to recognize that this is the multiplication of arguments. So what happens here is that I can write the multiplication of arguments as the addition of logs with the same base, making the equation even longer to write. You may want to pause the recording here and write that whole thing out. It may take you 5 or 6 minutes. I'll be here when you're back. Anyways, so because the reason why we can do that is because, again, we have the multiplication of arguments. And so logs make everything difficult and everything easy. So multiplication now becomes addition. And the reason why this is important is because the 365t is now on the entire argument for this log, so I can bring it down in front. Now I have a mess. However, log 2 divided by 8 is just a number. Log 2.4 is just a number. I don't know what that is, but my calculator does. 365 times log of 1.00100164384, that's just a number. As nasty as this equation looks, if it was this, 3x equals 10 plus 7x, everybody can solve this. We'd subtract 3x from both sides. We'd subtract 10 from both sides and solve. That's exactly what I have here. I have a number times the variable, like 3x. Well, this is log to base 10 of 2 divided by 8. It's not a nice looking 3, but it's just a number. Equals another number, not 10, that'd be nice. It's log 2.4. Plus another number times the variable. This number here is 365 times log of blah, 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 blah. So my calculator can handle this. I'm going to evaluate the logs here. Now I'm simply going to collect like terms. As nasty as this looks, I'm going to subtract this value from both sides. Now I'm going to add those values or subtract those values and divide. So this means that in 32.86 years, they will have the same amount of money in their accounts. Now, we can check that by plugging in the 32.86 into the time values. When we do so, we see that we are almost equal in value. The reason why we're almost equal is because this 32.86 is a rounded value. And that means that these will round to be $4,310 each. And that way we see that we have them correct. So folks, that's a tricky question for sure. I think it's the hardest question we do in the course. Not so much to set it up. This equation here you set up a dozen times and same for the other one. Then we set them equal to each other. Then what we have is some complicated numbers, and we have to remember that the exponent, this 365t, couldn't come down on both because we still have this coefficient here. So we had to separate that using the addition of logs. Then we could bring it down. Then it became a question that we could solve. So I encourage you to look back on that, maybe go through that a couple times. Make sure you can do that one because, like I said, it is tricky. Okay, next week we'll do some probability and then the receptor file. Let's see.